In the previous section, we have discussed decimal as well as binary numeral systems. Decimal system is a numeral system with base 10 and binary numeral system is with base 2. Similarly, we can define numeral systems having base b, where b may be integer 2, 3, 4, etc. Now let us consider a non-negative integer, say n. We need to find the base b representation of this number n. Let us suppose that n can be expressed as dk minus 1, dk minus 2, etc. d2, d1, d0 in base b. Then we are assuming that these numbers dk minus 1, dk minus 2, etc. d0, these digits are from the set 0, 1, 2, etc. b minus 1. Since we are considering the numeral system with base b, here if dk minus 1 is non-zero, we can say that n is a k digit number in its base b representation. Now, since the base of the system is b, the positional values will be, for the rightmost digit it will be b raised to 0. The second digit d1 from the right will have place value b raised to 1. This will be b square and so on. dk minus 2 will be having place value b raised to k minus 2. The place value of the digit dk minus 1 will be b raised to k minus 1. So we can express n as the sum dk minus 1 into b raised to k minus 1 plus dk minus 2 b raised to k minus 2 plus etc. plus d2 into b square plus d1 into b raised to 1 plus d0. We need to find these digits dk minus 1, dk minus 2 and so on, d0. What happens when we divide n by our base b? Then the quotient will be dk minus 1 b raised to k minus 2 plus dk minus 2 b raised to k minus 3 and so on, d2b plus d1, and the remainder will be d0. Thus, in step 1, we divided n by b and obtained some quotient, say n1, and remainder d0. We used the label n1 to denote the number dk minus 1 b raised to k minus 2 plus dk minus 2 b raised to k minus 3 plus etc. plus d2b plus d1. If we divide n1 by b in the second step, that is the dividend is n1 and the divisor is b here, then we will get quotient as dk minus 1 be raised to k minus 3 plus dk minus 2 be raised to k minus 4 plus etc. plus d2, and the remainder will be d1. And let us denote the quotient here by n2. Then in the second step we obtained the quotient n2 and the remainder was d1. And similarly in the third step, if we divide n2 by b, we will get some quotient, say n3, and remainder will be d2, and so on. Thus in the k minus first step we will be dividing nk minus 2 by b to obtain the quotient nk minus 1 and remainder dk minus 2. Then nk minus 1 will be of the form dk minus 1 into b, so that in the kth step quotient will be 0 and the remainder will be dk minus 1. Thus the process stops when we obtain 0 as the quotient. Note that in the first step we obtained the least significant digit d0 as our remainder, and in the last step, in the kth step, we obtain the most significant digit, that is dk minus 1, which was the leftmost digit in our base B representation of n. dk minus 1 is the leftmost digit, that is the most significant digit in base B representation of n, and d0 is the least significant digit, that is the digit in the ones place of n in its base B representation, and that was obtained as a remainder in the step 1. Thus to retrieve the base B representation of n, we need to write the remainders in reverse order, that is in the upward direction. dk minus 1, dk minus 2, etc. d1, d0 gives the base B representation of n. This method can be applied in the case of conversion to binary or conversion to any numeral systems with base B. We can use this repeated division by base B method. Now let us convert an integer, say n equal to 257, to binary system. We need to repeatedly divide this number by the base 2 here. We know that 257 divided by 2 will give quotient 128 and remainder will be 1. If we divide this number 128 again by 2, we will get 64 as the quotient and remainder will be 0. 64 divided by 2 gives 32 as the quotient, 0 will be the remainder. 32 divided by 2 gives 16 as the quotient, 0 is the remainder. 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 gives 2 as quotient and 0 as remainder. If we divide 2 by 2, we get 1 as the quotient, 0 as the remainder. 1 divided by 2 produces the quotient 0 and remainder will be 1. Thus finally we got 0 as the quotient, and the process stops here. And as we have observed in our algorithm, we know that 1 here, which is the remainder we obtained in the first division, will be the least significant digit in the binary representation, and this 1, the remainder in the last division, will be the most significant digit in the binary representation of our number. So we will need to write these numbers in the reverse order, that is in the upward direction. Thus we obtained the binary representation of 257 as 1 0 0 0 0 0 0 0. That will be 7 zeros after 1, and then the least significant digit 1. We can write 2 as a subscript here to denote that the number is in its base 2 representation. Now it's time for some homework. Convert the following numbers into binary. First one is 355. Second one is 101. Third one is 37. Okay, let us try another problem. Let us convert 160 to the base 7. Here also we can use the method repeated division by the base 7. Now if we divide 160 by 7, we will get quotient 22 and remainder will be 6. 22 divided by 7 gives 3 and remainder is 1. 3 divided by 7 gives quotient 0 and remainder is 3. Here also we obtain the most significant digit 3 in the last step. So we need to write down the remainders in the reverse order, in the upward direction. So 160 will be equal to 316 in base 7. Next question is to convert 10 raised to 6 to the base 26. In base 26, the digits used will have values 0, 1, 2, etc. up to 25. So there are 26 digits involved here. So it will be convenient for us to represent each of these values by the letters in English alphabet, so that 0 can be represented by A, 1 can be represented by B, 2 by C, and so on, 25 by Z. To convert a number from the decimal system to base 26, we need to divide the quotients by 26 repeatedly, as we have seen earlier. Let us consider the number 10 raised to 6 divided by 26. 10 raised to 6 by 26. You can use calculator, and here the integer part of this result gives us the quotient, that is 38,461. 38,461. Now to find the remainder, we need to subtract the integer part from the result. Then we should multiply fractional part by the divisor 26. We got 13.9999 etc., which is approximately equal to 14. This difference is due to the truncation of fractional part in the result displayed in our calculator. Now let us divide 38,461 by 26. Our quotient is the integer part 1479. Division by 26 gives the integer part 1479. To find the remainder, we will be subtracting 1479 from this result and then multiply it by 26. Here also the remainder will be equal to 7, since the difference is caused by the truncation of fractional part in our result. We can write 7 as our remainder. Now we need to divide 1479 by 26 gives 56 as the quotient, and to find the remainder, let us subtract 56 from the result and multiply the fractional part by 26 to obtain the remainder 23. Now let us divide 56 once again by 26. 56 divided by 26. The quotient will be 2. To find the fractional part, let us subtract 2 from it and multiply 26 to the fractional part to obtain 4. So our quotient is 2 and the fractional part is 4. Dividing 2 by 26 gives the quotient 0 and the remainder will be 2. 14 is equivalent to O. 7 is equivalent to H. 23 is represented by X. 4 is represented by E and 2 is represented by C. So that the representation of 10 raised to 6 in base B will be CEXHO in base 26.